All right, everybody, so this is the temporal ecology lecture looking at assembly rules. So this is expanding the time frame a little bit rather than seasonal. We're thinking about how, the patterns that we see found in a developing community, a community starting basically from scratch and developing in species establishing. So what assembly rules, then the study of assembly rules is looking for patterns or non-random patterns of community development, deterministic pathways of community development, basically any type of, let's say we have an empty habitat. As species come and start living there, do we see any patterns? And you might think about, when we're talking about spatial ecology, we're looking at this habitat selection model where we're looking at, species getting there, and then are the conditions right for them? Is there realized niche there? And then we get a community there. And you might say, well, isn't this just looking at assembly rules? And the answer to that is no. Why it's no is a little bit more confusing, but when we're thinking about this habitat selection model, the habitat selection is really a deterministic process. You would get the same results every time. And it's more of like a retrospective thing where we, start here, and then we can see why certain species were left out, why certain species, or I should say, why certain species didn't have their food sources, why certain species didn't have their fundamental niche, and why species never got there in the first place. Whereas assembly rules is kind of starting here and then going that way. And the thing is, when we're looking at assembly rules, what it really does is it de-stresses the species and essentially the habitat identity, the species identity and the habitat identity. So it's more like, okay, we have a given habitat, an empty habitat, a new lake, a new volcanic island, a new whatever. How do we expect that community to be built up? And what are the patterns that we see with that? Across the board, it's not necessarily just looking at a specific type of habitat. What are the overarching rules that the ecology kind of follows when any community is in itself assembling? Now, let's kind of just go through examples of this, and you can see how this plays out. One example of an assembly rule is just a R-star assembly rule. So it's for an invasion to be successful, the invader needs a lower R-star than current inhabitants. Okay, so what we got up here is this is that Tillman R-star model, right? Where we kind of talked about this before, but if the yellow species were to get there first, the blue species, since it has a lower R-star, should be expected to be able to colonize. However, if the blue species were to colonize first, that doesn't, it might not mean that the yellow could get there. You would need enough time essentially for populations to get big enough for this resource to get down to the R-star level of the blue species. So you would need populations essentially to be big enough. So we're talking time scales of potentially tens to 20s of years here, but what this then assumes is, given enough time, the species with the lowest R-star dominates. Now, we know that to not be true, right? There's plenty of examples, due to varying environments, where the yellow species would do just fine to be able to coexist with the blue species. And maybe the yellow species would dominate because there's enough time for the resources to fluctuate back and forth here on this x-axis. But it also assumes that competition for a single resource is really the only factor influencing assembly, and absolutely we know that to be incorrect, right? But it's at least the start of getting us an idea of some patterns that we would expect to see kind of across the board, no matter what type of habitat we're thinking about. Another example of an assembly rule is looking at guild filling rules. So what we would expect is that there should be the highest competition between species in the same guild. Now, guild is a little bit of a funny word, but what we're looking at is kind of like ways in which organisms do things. So in aquatic systems, what we have this thing called functional feeding groups. Now, functional feeding groups are ways in which organisms go about finding their food, right? So shredders are taking leaves and shredding up the leaves and eating the bacteria off those leaves. Filter feeders are literally filtering the water and picking out the phytoplankton or the poop or whatever they're eating. Scrapers and grazers, they're looking at eating the periphyton that's growing on top of rocks or wood or something, or hard substrates. Collector gatherers then are looking at how to finding food just that's deposited out everywhere. That's basically think about food particles that are dropping out onto the sediment. And then predators are organisms that are going around trying to murder everything else that I just talked about. Now, so if we had a certain type of mayfly and a snail, those mayflies are going to be scrapers. They are going to compete a lot with each other, right? So a snail on top of a rock licking off that periphyton is going to be fighting for space and competing with space with that mayfly over that same periphyton. And, essentially those scrapers are going to be found in the same spot, but they're not going to be found next to shredders, right? So shredders, unless they're some sort of weird indirect kind of thing, shredders don't really compete with grazers. Even filter feeders would be the herbivores, and same with these scrapers being herbivores. They're not going to be found in the same spot, and they're not going to be going after the same food sources. So there's really not going to be competition. So if you think about it in a grander sense, think about a stream, a new stream that comes by. Okay, essentially, anytime you get an empty guild, right? So what's the first thing to come in within the macroinvertebrate community? Anytime that there's an empty guild where there's essentially, let's say, no collector gatherers in the system, it's very, basically any collector gatherer that comes in there, if the conditions are right, are going to be able to use that untapped resource and take up that guild and start doing their function. So what we see then, what that leads to then is it's more likely, all else being equal, if you just kind of throw a bunch of species at an empty habitat, it's more likely that species in different guilds will establish early in the assembly. So what that's kind of saying is that there's going to be periphyton, there's going to be phytoplankton, there's going to be leaves in the stream, and there's going to be a bunch of organic matter in the stream. So early in that scenario, what you'd expect is one collector gatherer, one shredder, one filter, and one grazer, and then so those things would expected to be all of the guilds would expected to be filled up before you would essentially have two collector gatherers. But and so what we would see is that basically guilds would fill together at the same rate, and what that leads to then is this proportion of species from different guilds remains constant. Okay, and so let's not necessarily think about the predators because that's a little bit more confusing, but essentially what you would get is one grazer, one collector, one shredder, one filter feeder, and then you would get two grazers, two collector gatherers, two shredders, two filter feeders into the system, and then you would get 3, 3, 3, 3, and it keeps the number of species in each guild proportional, or just it keeps that proportion constant throughout time. And this isn't necessarily it isn't just like 1 1 1 1 2 2 2 2, but it's generally equal through time. Right, the next one I want to talk about is a checkerboard pattern. Okay, this is an assembly rule that we would expect to see when the habitat is broken up into distinct patches. Okay, now there's lots of examples where congeners, those are species in the same genus, different species, same genus, where they compete really strongly with each other, basically because they're so closely related. Maybe they recently speciated or something. So the congeners would be expected to compete most strongly. And what we see is oftentimes with these really strongly competing congeners, we get this checkerboard pattern. Now, it isn't necessarily like an exact checkerboard, right? But it's here we have the black species winning. Here we have the white species winning. Because they're so strongly competing, you never get a gray patch where you would have a black and a white species together. It's just one or the other. And so the order of arrival matters. In this case, what we see is we've got, I'm not even sure what the genus is of this species, but these are islands off of New Guinea. And there's Macinalei and Nigirostris. So just abbreviated as M and N. And what we see here is there's plenty of islands that have neither. But there are essentially species M and species N never overlap in where they're found, and then we get the MMM, MMM, N, and it looks kind of like you can analogize this to a checkerboard where you have one species there but never finding the other species because they're competing so strongly. One of the last community assembly rules I want to talk about is community closure. Now this is kind of thinking about once you do have an established community, what happens when you take a species out? And what we see is deletions really cause cascading extinctions. Okay, so given this scenario, this little food web here. So here we have primary producers, here we have herbivores, here we have a predator, primary predator, right? And here's a secondary predator. So think about what happens if you were to delete a species from this food web. Now, if you were to delete species D, what would happen to the food web? Essentially nothing, right? Other than species D going away. Now, if you were to but if you were to delete species A, what would happen, right? Well, so D might lose half of its food source, but maybe species D could make it up by feeding more on, well, we'll just call this species A, but essentially 100% of the food source of species B goes away, and 100% of the food source of species C goes away. So just deleting a single species, either through demographic stochasticity or maybe species A is, hunted out. So, maybe it's a prize hunting animal that goes away for a reason, or maybe species A was, killed by a big winter storm or something. What that causes then is cascading extinctions going on through the whole community, basically. Species B, so A, B, and C going away, and maybe the population of species D to really decrease due to half of its food being gone. So when we think about this in a restoration context, these communities can basically reorganize themselves. The food web reorganizes, and then it can close to either new or reintroductions. So think about it if species A did in fact go extinct, right? And we were really interested in species C because it's an endangered species. So what happens if you were to go into this community and just reintroduce species C? It would be doomed to extinction, right? So all your work would essentially go away because there isn't, there isn't species B, there isn't species A to funnel that energy up into the food web, up to the reintroduced species C. So when we're thinking about conservation, these assembly rules really need to be taken into context. So, if you're asked how to restore a degraded community, you can't just build it and expect them to come, right? Reintroducing these species and then hoping for the best just doesn't work, right? Nature has had really, really long periods to essentially work these things out, right? So when we think about a stream that we see today, it's essentially had eons of time for many, many invasions of different species coming in, getting established, going extinct, and you could essentially have a stream or a lake, well, not necessarily certain lakes, that are millions of years old. And the reason why we have those species there is because they've had so much time for this assembly scenario to proceed. And when we try to come in and do conservation and reintroduce species in, all at once, really what we should be thinking about is, well, what is the order in which we're bringing these species in? Do they have the correct resources for them? And if you were to think of this in a completely iterative process, the species richness, so basically what I want to say is that how many different scenarios can you expect? And so if you were completely doing this iteratively, you could, test to add in, first add species A, then B, then C. But then you could do species A, C, B. Or you could do species B, A, C, or B, C, A, right? So there's real quickly it gets huge, right? And the number of assembly sequences has to do with the species richness and then factorial, right? So, what you do is, let's say you had 3 species in a system, 3 factorial equals 3 times 2 times 1. You could have 6 assembly sequences, right? But just with 10 species, that's 10 times 9 times 8 times 7 times 6 times 4, so forth, you get over 3 million. And if you have 100 species, you would get 9.3 times 10 to the 157th, right? Numbers of possible assembly sequences. So coming into a system, like fixing the habitat, right? You got this degraded stream here to try, let's say we fix up the habitat physically to work right. And we, there used to be, 100 different species of fish, invertebrates, and plants. Just reintroducing everything all at once is just one of the ways out of 9.3 times 10 to the 157th, right? And what is the probability that that is going to work? Probably pretty low. So what this is saying is that thinking about conservation is oftentimes a really tricky thing. All right, with that, we'll leave it at that, and I'll see you later.